Hello and welcome to another AP Physics 1 review video. In this video we'll be talking about the concepts of SHM, or simple harmonic motion, and waves. So they're very much interrelated. Waves are just when we plot simple harmonic motion on some type of relative axis. Okay. So what is simple harmonic motion? Simple harmonic motion deals with three things. One, to deal with the idea that displacement, velocity, and acceleration vary sinusoidally of the thing that's wiggling. So what we mean by that is if we have something that's hanging down on a spring like this, and we pull it down to some distance and we let it go, it's going to go ahead and start wiggling.
Students who attended the ASVAB interpretation session are now returning to class. Thank you.
If we were to plot basically in terms of its displacement, acceleration, and velocity, we would see some different things. If it starts down at that bottom position, it would be here, and it would be changing like that. And it looks like a sine wave, a sine function. So if we were to look at that x distance over time, if we were to go in and deal with its velocity, we're going to realize at the start, when it's pulled back to that point and let go, it's going to have a small velocity. And after it goes through, it's going to have a large velocity when it's here in the middle, right when it's in the x-plane there, at x equals 0. And it's going to be decreasing, once again, at those points there. So we find it does show some relative sine functions. So that would be the velocity time graph. Again, they look very much sinusoidally. Then if we were to deal with the acceleration in time graph, we realize that's going to happen, max acceleration is going to be at those relative ends. You say, well, why is that going to be holding true? Well, yes, but it's going to be, we have a negative x here, but we're going to have a large positive acceleration at the top. So basically you look at the negative of the cosine function that we see on the top. So something like this, right? Cool. And the other thing we could do is we can plot those along those same points to realize what's happening when it's in the middle and all those different things. If we look at our equations we use within this unit, they look at kind of a little bit silly, a lot of things going on. And we look at this one, this A is A cosine 2 pi ft. What is that? That's dealing with the sinusoidal oscillator, basically something wiggling at a constant period with a constant restoring force, okay? And its x position could be modeled with this function by using that cosine. Again, we look at this, we can see what's going on there. Now, that A stands over the relative amplitude, the distance that I bring it back from its equilibrium position. Now, one thing that's different now in terms of just pulling things back in terms of Hooke's law is we're saying, okay, we have something, it's pulled and it's just sitting there. Like if we had a spring hanging down, that is not now the x position. The x position is now where we pulled it from its hanging point. So now our equilibrium point has actually changed a little bit. If you're not sure exactly what I'm referencing there, make sure you're clear on the ideas of Hooke's law as well as on the idea of a simple harmonic oscillator, a spring wiggling. Okay? Okay, so we can see that we have those three different ideas and they seem pretty much okay as long as we graph them and see what's going on. Two, we see that acceleration is proportional to displacement but in opposite direction. Do we find that here? Well, hey, notice at those ends, we do have large accelerations, but they're negative. Again, that shows to be a negative cosine function. And lastly, the frequency and the period are independent of the amplitude. Now, you notice in this case, the wiggle, as this happens, we find that amplitude doesn't show up here. How could we look at amplitude on these graphs? It'll be from a distance from x here. Now, if you notice what's going on here, this x position.
Stand attention, please. Will all support staff members please come to the office to sign your timesheets? All support staff, please come to sign your timesheets.
We notice this x position is related to amplitude. Yes, I agree with that, but it's not related to how this thing happens. Now, we saw that in a lot of different labs within the course. And what I'm trying to stress is the fact that the amplitude does not affect the period. For the same reason if we deal with a sound wave. If you increase the volume on a sound being played, it doesn't travel faster. If that was to hold true and you were to turn up the volume and walk away from the speaker or stay in a different position, the low beats and the high frequencies would go ahead and reach you differently. That does not happen. The amplitude does not affect the frequency. Again, amplitude does not affect frequency. That's one of the big things that we're seeing here. And also relating that to the idea of period, to deal with the ideas of frequency and period, T is 1 over F. They're inverses of each other. So if something wiggles 2 times per second, that means the frequency is 0.5 hertz, 1 over 2. Okay, the other ideas that we see within the simple harmonic motion unit, we find the period of a spring, the period of a wiggler, a spring wiggler, is 2 pi root m over k. We find it's dependent on the mass being wiggled, And K, which is the spring stiffness constant. We find, once again, in there, no A, no amplitude. Doesn't matter how far I bring this thing down, still wiggling at the same rate. The period of a pendulum, 2 pi root L over G. Now, if you kind of think to yourself, these are common multiple choice questions that pop up a bunch. How can I remember that length of a period, length of a pendulum, that the mass doesn't matter? If you think about the idea of rotational inertia. The longer we made that mass from the outmost point, it was more difficult to spin, rotate. Same thing holds true with the period of a pendulum. The longer that length is, the longer that pendulum becomes. We notice that, once again, the amplitude, the distance I pull that thing back does not matter. That does not matter. You could be asked a free response question, could you take a pendulum, a bob, a mass at the end of a string, and let it go? And could you find the gravitational pull, the gravitational acceleration from that? Well, most certainly. If you went ahead and timed it, talked about that experimentally, the length of the string in order to find G. Not that crazy to do. Now, the other equations that we see in here are Hooke's law. F is equal to negative kx. That's the spring constant. We could go ahead and do that. You could be asked to do that in terms of a short answer question to find that experimentally. And we find that the energy stored in a spring is equal to 1/2 kx squared. I realize that we've talked about that a little bit in terms of the energy ideas from earlier. Okay, the other part of this deals with wave stuff. So if we take a spring oscillator like this and we let it go, we propagate it, and we were to track its motion, we find a wave. Duh, we find this stuff here, right? This kind of looks like a wave, right? So wave stuff is pretty cool. We've got two types of waves that we can look at. We can look at longitudinal and transverse. Longitudinal waves occur if we have some type of compression and refraction. I know I'm trying to overemphasize this. This is if I push a pulse like this, we can have some compressions and expansions. Transverse is where we find wiggles like this, that they move like this down a plane. Now, the cool thing with these waves are they can interact with other waves. So if I have a wave like this, and a wave like this, and a wave like this coming towards each other, they'll actually go ahead and build a larger wave. Neat. We call it constructive interference. If I have a wave like this, and a wave like this coming towards each other, they'll actually partially cancel out. If they're of equal size, they'll actually completely annihilate each other. Then afterwards, they'll go ahead and they'll be traveling through. That's the point you want to make. They don't completely just kill each other out and die. They go ahead and they cancel each other out at that point in time, but then continue moving up. We saw the same thing with beats for tuning forks. Tuning forks with very similar frequencies can actually create that sound that we heard within the lab because of that partial cancellation annihilation. Now, when we have a wave get reflected back, it does some cool stuff. Depending on how it gets reflected back, we can have an increase in the overall amplitude because of that interference. And that can happen either within a closed system, or a single closed system, or an open-ended system. And what I mean by that is this. So this is something that we did, and this is something you need to be aware of for the exam, because this is kind of a textbook, multiple choice question that will indeed happen. If we look at these 3 different examples, I'm looking at all these different harmonic functions as we see here. Now, you may say to yourself, well, what does this mean? What can we do with this? You could use V is equal to F lambda. The velocity of the sound wave, or any type of wave, is equal to frequency times the wavelength. You could be asked to do a couple different things with that. Now, looking at each one of these situations, they're not all the wavelength. So, if we take a look at what we see here, in a double open system for this first harmonic, if we were to continue this thing out and see, okay, well, what is that? That's not one full wavelength. That's one full wavelength. So this section here, as we see it, is indeed 1/2 the wavelength. 1/2 the wavelength for that first harmonic. In this case, for a double open here, well, hey, that's definitely the full wavelength, right? Then we find in the third harmonic here, there's okay, there. Oh, cool. That's one full wavelength, and there's another half, right? Cool, right? Doesn't seem to be all that bad. Cool. Now, in reference to that idea, that deals with a double open like that. Now, that You say, when does that thing happen? Maybe blowing through a tube or something like that. But when really you see it within the lab is something hitting a boundary which reflects that wave. So hitting water or something like that. So that's where you normally see an open closed tube. So what is this? You say, okay, that looks kind of weird. If I go through the end here, well, that's now to half. And if I was to continue through, so that what does that mean for this? That means that what I actually have here is indeed 1/4 lambda, which sounds kind of weird. Now, in our next one that we can go ahead and see, and this is not a full wavelength either, right? We find that here to here, well, that's 1/2. So this whole thing here, 3/4 lambda. Weird. And in our last one, as we reference it here, this would be, that's a full wavelength. So in this case, this is indeed 5/4 lambda. Cool. Now, again, in terms, that could be an easy experimental type problem. It can be shown up as as a multiple choice question in dealing with standing wave and wave reflections. Again, textbook ideas to make sure that you can remember within this idea are dealing with these types of graphs for dealing with some type of oscillator. The idea that amplitude does not affect the period, or equations for a period of a spring, a period of a pendulum, and remembering the standing wave functions for double open and partial open systems for standing wave functions. As always, thanks for watching. See you in the next video.